Hello friends, welcome to Knowledge Galaxy to rediscover the basics with Mayank Tiwari, a premier coaching and training channel dedicated to metallurgy studies and consultancy. Established to cater the needs of students, degree, diploma and AM/IIM metallurgy, competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals and whosoever seeking knowledge and information about various subjects and topics of metallurgy, ferroalloys, operational process optimization, productivity improvement analysis, etc. To impart practical industrial knowledge as per your specific requirements via tailor-made training sessions for your colleagues, employees and students, please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +919907144101 for scheduling and organizing the sessions at your place or via video conferencing. My dear friends, nowadays technology has improved so much that actual physical distance doesn't matter anymore. You can get all your doubts cleared by sitting at your home, at your comfort zone, just by contacting me over WhatsApp or phone, so that for your benefit, please do contact me for any of your doubts. My dear friends, I have made so many videos which are available on my YouTube channel. So I request you to visit my channel regularly and repeatedly and watch all the videos available there, so that you can gain maximum knowledge about the subject and topics, and also request you to watch all my videos from start to finish, so that you can gain the maximum and complete knowledge about the topic. My dear friends, as you know that training is costly, but not to train is still costlier. And when you are not having complete knowledge or don't get any information about the topic which you need to know, so you can contact me. If you don't find anyone who can help you to clear your doubts, you do contact me as soon as possible. And so right now in this video I am discussing about In this video, I am going to describe about yet very important and fundamental topic of ferroalloy production, and the title of this presentation is Carbothermal solid state reduction of manganese ores. Since manganese-based ferroalloys are the backbone of most of the steels produced worldwide, be it ferromanganese, be it silicomanganese and other forms, so it is very much necessary to know about how the carbothermal solid state reduction of manganese ores happens in actual practice, and what is its significance and how it affects the overall productivity and cost of production of ferroalloys. So before proceeding to the details of this presentation, I would like all of you to go through the videos given in the next slides and observe the message given in these videos. and observed in the video that no water can be filled in the pot if the pot is not aseptic, and also if the pot is already filled. The water can only be filled when there is some space in the pot. So, my dear friends, I request you to keep your minds open for receiving the information so that you can receive the information correctly and gain the knowledge. But if you feel that you are already having much knowledge or more knowledge, or if you are not receptive towards receiving the new knowledge or information, you cannot gain anything. So for gaining new knowledge and information, please keep your mind open and be receptive for the new knowledges always. My dear friends, I am having one of very important announcement for you all. The information which I want to share is that if you want to advertise your products, services, company or anything else on my channel, then please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +919907144101 for putting your advertisements in my forthcoming videos. My dear friends, as you all are aware that advertising in the YouTube channels is very common and very fruitful method of approaching to the mass volume of viewers. So you can contact me for putting your advertisements in my forthcoming videos. I hope the messages given in the previous slides are very much clear to you all. So now let's start this presentation with a synopsis. So in this synopsis, I will be briefly describing about the detailed project presentation which will be followed later. So this is the synopsis of this presentation. To start with, carbothermal reduction of manganese oxides and manganese ores in the solid state was studied in hydrogen, helium and argon at different temperatures, ore compositions and carbon to manganese oxide ratios. Vessels ore from South Africa and two grades of the Groote Eylandt ore Australia with different levels of impurities were examined. Ores were characterized by X-ray diffraction, X-ray fluorescence, optical microscopy and scanning electron microscopy. Isothermal and temperature programmed carbothermal reduction experiments were conducted in a fixed bed reactor in a vertical tube furnace with online monitoring of gas composition by the CO2 infrared sensor. The reduced samples were characterized by X-ray diffraction, SEM and LICO analysis. Extent of reduction was calculated using data on the off-gas composition and LICO carbon and oxygen contents in the reduced samples. Manganese oxides in the ore were reduced to alpha manganese and carbides, that is Mn23C6 and Mn7C3, depending on the carbon to ore ratio. The reduction rate of manganese ores in hydrogen was higher than in helium and argon. So now we will be having the introduction and go deep in the presentation step by step. Carbothermal reduction of manganese ore is the major industrial method for processing of manganese ore and has been intensively studied. It is well established that manganese oxide is reduced quite slowly in the solid state. That is why in the industrial production of manganese alloys,
in blast or electric ferroalloy furnaces, the reduction or smelting temperature is around 1500 degrees Celsius, at which manganese oxide is reduced from the molten slag. However, manganese oxide in manganese ore exists in the form of a separate phase. In the smelting reduction of manganese ore, manganese oxide is firstly dissolved into the molten MnO, SiO2, Al2O3, CaO, MgO slag and then is reduced from the slag. Reduction of manganese oxide from the slag is strongly retarded by silica and is slower than the reduction of pure manganese oxide. Reduction or pre-reduction of manganese ore in the solid state, if it is implemented at a reasonable rate, can improve efficiency of processing of manganese ore. Effects of temperature, ore composition and size are quite well established. The effect of gas atmosphere on the carbothermal reduction of manganese oxide and manganese ore has been studied to a lesser extent. Ding examined the effect of the partial pressure of carbon monoxide on the manganese ore reduction. He stated that decreasing the carbon monoxide partial pressure by about 2/3 is equivalent to a temperature increase of 60 to 70 degrees. Zerwin and Olsen also found that lowering the carbon monoxide partial pressure enhanced the rate of reduction. Eric and Buruku compared rates of MnO reduction by graphite in different gas atmospheres in argon, carbon monoxide, carbon dioxide and by CO. They showed that the argon and carbon combination gave the greatest rate and extent of reaction, followed by the other systems in the order above.
My dear friends, just to interrupt you all, here I would like to emphasize on some special important aspect of Knowledge Galaxy. Here, specialized subject-wise coaching classes and topic-wise doubts clearing are available. I am available for all of you to clear all your doubts, and especially for Diploma Engineering, Metallurgy and Mechanical students, Indian Institute of Metals, that is IIM, Part 1 and Part 2, and competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals. Here I would like to emphasize that whatever queries and doubts you are having in your mind regarding any subject or topic of metallurgy or any other ferroalloys production, operation, maintenance, so you can contact me for getting your doubts cleared. I will try to provide you accurate knowledge and to the best possible extent at the very shortest period of time, so that you can gain your knowledge, clear all your doubts, so that you can grow in your career, whether it is academic career, whether it is of professional career, and so that you can develop and grow. So to continue with, here complete syllabus coverage for the students aspiring to appear in the forthcoming semester exams, that is December or June, I will be providing you all. So please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 44 101 for scheduling and organizing the classes or getting informations to clear your doubts via video conferencing, call or WhatsApp. My dear friends, you might have encountered that you might have been having many of the doubts regarding process, technology, why they are doing, why it is done, how it is done. So, and if you don't find any answer to them and nobody is there to guide you properly, so my dear friends, I am here available to guide you all, to make you know and grow, and so that you don't have any doubts related to your process, products, technology, syllabus, and I will make sure that all of your doubts get clarified and you know the topic and subject very well and completely. So again, let's move on.
Data obtained by Terayama and Ikeda for carbothermal MNO reduction in helium showed that MNO is reduced much faster in helium than in argon. Similar results were obtained by Yastreboff et al. For MNO, manganese ore and ferromanganese slag. The strong response to changing the atmosphere to a different inert gas with different diffusivity provides an insight not only to the reaction mechanism but also to the identification of limiting stages. So this paper examines carbothermal reduction of MNO and manganese ores in argon, helium and hydrogen. No previous work on carbothermal reduction of manganese oxides or manganese ore in hydrogen has been published to my knowledge. The paper presents experimental results on the carbothermal reduction of MNO vessels ore from South Africa and 2 grades of Glute Islanded ore from Australia. So now we will discuss about the experimental findings. Samples were made by mixing pure MNO or manganese ore with graphite. The manganese monoxide was in powder of 60, -60 plus 170 mesh with a purity of more than 99%. Synthetic graphite, that is CAS 7782-42-5 in a powder of less than 20 microns was mechanically mixed with manganese oxide MNO with varied MNO by C ratio. The investigated manganese ores were Glute Island, Australia and Wessels, South Africa ores. 2 grades of Glute Island were studied. First one is Glute Island Premium Sand with high silica content GE-PS and Glute Island Premium Fines GEPF. Manganese ores were preheated in air at 1000 degrees Celsius for 3 hours. Results of XRF and LICO, that is oxygen analysis of preheated ores, are shown in the table in the next slide. The examined ores had a fraction of plus 45 minus 150 microns. So this is the table 1 which shows the chemical analysis of preheated ores in weight percentage. You can pause the video and observe the different table contents. Okay, now moving ahead. Reduction experiments were conducted in an alumina reactor in the vertical electric furnace. The furnace gas atmosphere was made from pure hydrogen, helium or argon. Brooks mass flow controllers with electronics were used to regulate gas flow rates. A powder sample was placed into a graphite crucible with 10 mm diameter and 21 mm height. The average sample mass was 1 gram. The exit gas was analyzed using CO-CO2 infrared analyzer and dew point monitor. Phase composition of samples was characterized by X-ray Siemens D5000 diffractometer with nickel filtered copper K radiation. Copper K means copper potassium radiation. Now I will discuss the results of the experiment. Carbothermal reduction of pure MnO in different gas atmospheres. This is the first subtopic of the results. Carbothermal reduction of pure MnO in hydrogen, helium and argon was studied in the temperature range of 1050 to 1400 degrees Celsius. Reduction in hydrogen was examined at different MnO by carbon molar ratios. Figure 1, which is presented in the next slide, shows reduction curves at 1200 degrees Celsius for the MnO by C molar ratios in the range of 1 by 0.34 to 1 by 2. Reduction behavior was not affected by the MnO by C ratio when it was below 1 by 1.22. However, this ratio had a strong effect on the phases formed in the course of reduction, which is shown in figure 2. Table 2 summarizes the results of XRD analysis in figure 2 of samples obtained in the MnO reduction in the temperature range of 1200 to 1300 degrees Celsius with different MnO by C ratios. So this is the figure 1 which describes about carbothermal reduction of MnO samples with different MnO by C molar ratios at 1200 degrees Celsius in hydrogen. You can pause the video and observe the figure contents. For samples with MnO by C ratios more than 1, the main phase was MnO. Only a small amount of manganese carbide Mn23C6 and alpha manganese was observed. When the molar MnO by C ratio was in the range of 1 to 1 by 2 or smaller, no oxide phase was detected. The main phases were alpha manganese and Mn23C6. Reduced samples with MnO by C less than 1 by 1.5 contained only carbide phase Mn7C3, which is shown in table 2. No residual carbon was observed in a sample produced in the reduction with MnO by C ratio 1 by 1.3 and above. The stoichiometric MnO by C molar ratio for complete conversion of MnO to Mn7C3 is 1 by 1.43, that is 7 by 10. The XRD examination of samples with MnO by C ratio below the stoichiometric value in the course of reduction revealed, which is shown in figure 3, that reduction of MnO proceeded to Mn23C6 through the high carbon manganese carbide Mn7C3. The final product depended on the MnO by C ratios which is shown in table 2 and was independent of the gas atmosphere. For a sample with MnO by C ratio equal to 1 by 1.3, the formation of Mn7C3 carbide was completed in 60 minutes when the degree of reaction reached 91% reduction and all carbon was consumed. This reduction stage can be presented by the equation. So this is the table 2 which I have just explained. Table 2 shows that phases formed in the carbothermal MnO reduction with different MnO by C ratios. And this is the graph, figure 2, XRD patterns of reduced MnO samples with different MnO by C ratios in hydrogen and helium in the 1200 to 1300 degrees Celsius. Okay, moving ahead. MnO, the reaction given is MnO plus 1.3 C is equal to 0.13 Mn7C3 plus 0.91 CO plus 0.09 MnO. This is the first equation. Further reduction proceeded in accordance with the equation 2 which is given below. 0.09 MnO plus 0.097 Mn7C3 is equal to Mn23C6 plus 0.09 CO. This is the equation number 2. Reduction curves for carbothermal reduction of MnO with MnO by C ratio of 1 by 1.3 in hydrogen in the temperature range of 1050 to 1400 degrees Celsius are presented in figure 4 in the coming slide. In all gases, reduction rate increased with increasing temperature. So this is the figure 3 which shows the XRD patterns taken at various stages of MnO reduction in hydrogen with MnO by C ratio 1 by 1.3 at 1200 degrees Celsius, which I have just mentioned. And this is the figure 4 which shows the carbothermal reduction of MnO at different temperatures in hydrogen having the MnO by C ratio of 1 by 1.3. You can pause the video and observe the different graphs and its pattern, how it is moving. Effect of gas atmosphere on MnO reduction at different temperatures is shown in figure 5 to 7 in coming slides. Reduction was fastest in hydrogen and slowest in argon. However, effect of gas atmosphere depended strongly on the temperature. Reduction in argon and helium at temperatures 1275 degrees Celsius and below was slow and incomplete. Only reduction in hydrogen was close to completion at 1200 degrees Celsius. However, the difference in reduction behavior in different gases decreased with temperature. At 1400 degrees Celsius, reduction curves obtained in hydrogen and helium were almost identical as shown in figure 7, although reduction in argon was slower than in hydrogen and helium. So this is the figure 5 which shows the reduction curves for samples with MnO by C ratio equal to 1 by 1.3 at 1275 degrees Celsius in different gas atmospheres. And this is the figure 6 which shows reduction curves for samples with MnO by C ratios equal to 1 by 1.3 at 1300 degrees Celsius in different gas atmospheres. And this is the figure 7, which shows reduction curves for samples with MnO by C ratios 1 by 1.3 at 1400 degrees Celsius in different gas atmospheres. I have just described all three curves, so please recall that. Now, next step is carbothermal reduction of manganese ores. In the reduction of manganese ores, the effect of the ore to carbon ratio by mass was studied at 1200 degrees Celsius in the hydrogen gas atmosphere. Reduction curves are presented in figures 8 to 10 in coming slides. Reduction curves for the vessels ore were in a relatively narrow band for the carbon content in the ore carbon mixture in the range of 12 to 30 weight percentage. So this is the figure 8, which shows the carbothermal reduction of vessels ore with different carbon content, that is in weight percentage, at 1200 degrees Celsius in hydrogen. Effect of carbon content on the reduction of Groote Island ores was quite minor when the carbon content was above 20 to 22 weight percentage. However, the carbon content affected strongly the phase composition, which is shown in table 3 in coming slide. Reduction curves for vessels, GEPF, GEPS, ores and manganese oxide in hydrogen, helium and argon at 1100 degrees Celsius and 1200 degrees Celsius are shown in figures 11 and 12 respectively. I hope you can recall the full form of GEPF and GEPS. I have already told this in the previous slides. At constant temperature, rate of reduction depended on the type of ore and the gas atmosphere. So this is the phase composition of reduced manganese ore samples with different carbon content at 1200 degrees Celsius in hydrogen. So this is the table 3 as mentioned above. You can pause the video and observe the contents. And this is the figure 11, which shows the carbothermal reduction of manganese ores with 38% carbon at 1100 degrees Celsius in hydrogen, helium and argon atmospheres. This is figure number 12, which shows carbothermal reduction of manganese ores with 30% weight percent carbon at 1200 degrees Celsius in hydrogen, helium and argon atmospheres. Under identical conditions, rate and extent of reduction of Wessel's ore were higher than of GE ores and of pure amino oxide. All ores reduced faster in hydrogen than in helium, and reduction in helium was faster than in argon. Reduction of manganese ores in helium and argon at temperatures 1100 degrees Celsius and 1200 degrees Celsius and in hydrogen at 1100 degrees Celsius was incomplete. So now let us have some discussions on whatever we have just gone through. It is accepted that carbothermal reduction by solid carbon proceeds via a gas phase. The overall reaction of amino reduction by carbon is given by the equation 7MnO plus 10C is equal to Mn7C3 plus 7CO. This is the equation number 3. Is presented as a sum of 3 reactions. Means this equation is presented as a sum of 3 reactions as mentioned below. First one, MnO plus CO is equal to Mn metallic plus CO2G. Equation number 4. CO2 plus C is equal to 2CO. This is equation number 5. Next is 7Mn plus 3C. This gives Mn7C3. This is equation number 6. The rate of the overall MnO reduction is suggested to be limited by the interfacial Baudard reaction or by transport of CO2 within the porous bed of the solid reactant mixture to the carbon particles. At high temperatures, when MnO is reduced from the molten slag, direct graphite molten slag reaction may dominate in the reduction processes. The rate of MnO and manganese ore carbothermal reduction is the fastest in hydrogen and is faster in helium than in argon. Strong effect of the gas atmosphere on the rate of manganese oxide reduction indicates that external and internal mass transfer of gaseous reactants may play an important role in the reduction kinetics. The difference between argon and helium is the degree of resistance that they impress onto the diffusivity of other gaseous species. Diffusivity of carbon monoxide in helium and argon calculated using the Chapman-Enskog formula at 1400 degrees Celsius and 1 atmosphere is 16.9 cm square per second and 3.6 cm square per second respectively. The difference is a factor of 4.7. Diffusivity of carbon monoxide in hydrogen and helium is about the same. Therefore, internal and external mass transfer is not a factor distinguishing carbothermal reduction of manganese oxides in hydrogen and helium. However, hydrogen is involved in the reduction process, reducing higher manganese oxides to MnO and iron oxides to metallic iron. In the presence of carbon, hydrogen can also reduce MnO to the metallic manganese. The equilibrium constant for the reaction can be given as MnO plus H2 gives Mn plus H2O. This is the equation number 7. And here log K is equal to minus 7394 divided by T plus 1.07. And it is calculated using data from Naked et al. Is below 10 to 3 even at 1500 degrees Celsius, and it is about 10 to 4 at 1200 degrees Celsius. However, the presence of solid carbon will maintain partial pressure of H2O at a low level by the reaction C plus H2O. This gives CO plus H2. This is the equation number 8. Log K is equal to 2.68 at 1200 degrees Celsius and log K is equal to 3.48 at 1500 degrees Celsius. What makes the reduction of manganese oxide by hydrogen in the presence of solid carbon feasible? Another possible mechanism of carbothermal reduction of manganese oxides in hydrogen atmosphere includes formation of methane as follows. C plus 2H2, this gives CH4. This is the equation number 9. MnO plus CH4, this gives Mn7C3 plus H2 plus CO. This is the equation number 10. My dear friends, please note and observe this equation as very carefully, because this equation provides two reducing agents, that is hydrogen and carbon monoxide. So it is very important to note and to keep in mind. Although partial pressure of methane in the gas phase is low, that is 0.01 to 0.03 atmosphere in the range of experimental temperatures, the carbon activity of the gas phase in equilibrium with graphite is unity, which is sufficient for manganese carbide formation. In general, solid gas reactions are faster than solid-solid reactions. Methane may act as a means for carbon transportation, what accelerates the overall reduction processes. I again repeat this. Methane may act as a means for carbon transportation, what accelerates the overall reduction processes. Higher MnO reduction rate in hydrogen than in helium and in helium than in argon indicates that the reduction rate was mixed controlled by the chemical reaction and internal and external mass transfer. At high temperature, that is of 1400 degrees Celsius, MnO was reduced in hydrogen and in helium with about the same rate, which was higher than in argon. This is an indication that at 1400 degrees Celsius, the reduction rate was controlled by the mass transfer, a role of hydrogen in reduction was insignificant. Reduction of manganese ores was strongly affected by the ore chemistry. Vessels ore contains much higher iron and calcium oxides and less potassium than both GE ores. GE is gluten islanded, that is from Australian ores, while GEPS has high silica content. Vessels ore contain 10.15 weight% iron, while iron content in GEPS and GEPF ore was 5.06 weight% and 3.58 weight% respectively. Iron oxides were easily reduced by hydrogen to metallic iron, which acted as mutely in the reduction of MnO. This can be one of the factors explaining faster reduction of vessels ore in comparison with GE and higher reduction rate of GEPS ores in comparison with GEPF. In the reduction of GE ores, manganese silicate was formed fluxed by alumina and alkali oxides. This silicate was liquid at temperatures above 1100 degrees Celsius. Formation of liquid phase hampered the reduction of GE ores. Vessels ore remains solid at 1200 degrees Celsius. Its carbothermal reduction in the solid state in hydrogen atmosphere reached above 90% in less than 20 minutes. So now we have reached to the conclusions, and now it's the time to sum up whatever I have described in this presentation. Carbothermal reduction of manganese oxide and manganese ores was strongly affected by the reduction temperature and gas atmospheres. Reduction of MnO in hydrogen was close to completion at 1200 degrees Celsius in about 2 hours, while in helium and argon, reduction of MnO was not completed during this reaction time at temperatures below 1300 degrees Celsius. Carbothermal reduction of MnO and manganese ores at constant temperature was the fastest in hydrogen and slowest in argon. Rate and extent of reduction of vessels ore were higher in comparison with gluten islanded ores. Composition of phases formed in the reduction process depended on the manganese oxide to carbon ratio and was independent of the gas composition. Carbothermal reduction of vessels ore is feasible in the solid state at 1200 degrees Celsius. I hope with this conclusion you must have got a full lump sum knowledge of full this presentation, and I hope whatever I have explained is very much clear to you all. If you have any doubt in understanding any of this thing, you can again contact me on given numbers, and my email ID is also mentioned, and this is my WhatsApp number. So if you have any doubt, you can contact me.
Dear friends, I am providing you all the informations free of cost which are available in my YouTube channel. So do help me by watching all my videos. Do subscribe my channel. Regularly visit and repeatedly visit my channel. Do watch all my videos contains like the content, share with your friends, and so that I also get motivated from each one of you as you subscribe to my channel. I am very much thankful to all my subscribers who believe in me, have subscribed my channel and like my content. So to motivate me further, please do subscribe my channel, increase the subscriber count, share with your friends so that others can also gain the knowledge. And my dear friends, all if you subscribe my channel, this will motivate me to do further better. So I hope you like the content and found the video worth. So again request you to please don't forget to like, share and subscribe the channel. Also remember to press the bell icon so that you can get the notification of the new videos promptly. My dear friends, here if you want to advertise about your product, services or company or anything else for gaining popularity in my channel, so you can contact me so that I can put your content for advertisement in my videos, forthcoming videos. So it will be a good platform to advertise. So do contact me as soon as possible. Thank you very much for watching this video till the end, and I am very much again thankful to all of you who helped me, who believe in me, and please do visit my channel regularly and repeatedly. Thank you very much again. See you in the next video. Thank you.